I'm taking food. I'm on a diet, so I can't eat carbs. It's gonna last a year. So sad. Where did I put it? Oh. My sketch work, my studying work. This organization is madness, okay? Yeah, I don't know when she's gonna start.
Okay, so we're starting a new chapter today, and this is kind of like I'm going to put a big chunk of what I'm presenting is not in the book. I want you to understand that it's going to appear in the next chapter we study, which is 15, but there is nowhere in the book that talks about them, except that they're using them. But since chapter 15 and 16 and 17 are these are the biggest chapters you have to study. They have the most functional groups: aldehyde, ketones, carboxylic acid, anhydrides, acyl halides, and the list goes on. So there are like 8 functional groups or 9 functional groups in these 3 chapters, and we're going to look at different reactions for each one of them. How are they similar? How are they different? So I'm presenting everything in a different way, but the questions in the book are still going to be relevant, so there's no problem with that. It's just the way I'm going to present it that's slightly different from the textbook. So first of all, this chapter is about organometallic, and I want to start with hydrides, which are not in the chapter, but for me, they're very similar to organometallics. So I'm going to do the first step of hydrides, then we compare them to organometallic, so that when you see them in all the future chapters, and they're going to appear almost in every single one of them, you understand how are they similar. So sometimes they don't explain it, but they assume you know. That's the reason they're not talking about them here. So what are hydrides, and what's the difference between hydride and organometallics? So that's really the basic thing about this chapter. What are organometallics? But before we get there, I want to start with hydrides. So to start with this, I want to show you a few compounds, organic compounds. And all compounds that we studied, they have a CH. Whether it's double bond, triple bond, it doesn't matter. You can have a CH that's either on an sp3 or sp2 on sp. Okay, these are chapter 6, 7. You have these. You also have the CBr or halogen. Okay, so that's also in chapter 9. We studied halogens, how they undergo substitution and elimination. Then you have the COH. Okay. Then you have the NH. So we studied these. This is chapter 10, the alcohols. They mentioned a little bit the amines in chapter 19. Now, why am I mentioning all of these? It's because all of them have a bond with an H. Okay? So, which one is more electronegative or which one pulls harder? If you look at carbon, it's 2.5. So in all of this is 2.5. Okay? You don't have to remember these numbers, doesn't matter really, but I just want to use them to explain a few things. Hydrogen is 2.1. We look here, for example, if I put F as a halogen, or Br, so the difference is still here 2.5, but this can be 4 if it's a Br. I'm just giving a couple, you don't have to have all of them, but if it's a Br, it would be, I don't know if I have that number, but yeah, it's 2.8. Here, it's really mainly, I'm looking at this bond. So this is 2.1, 2.1, and the oxygen is 3.5. I can also add an SH because we did this in the previous chapter. So the nitrogen here is 3. And here it's 2.1, and sulfur is 2.5. So why am I showing all of this? Is to show if these bonds break, which atom would take the hydrogen? Is it the H or the other atom? So here, should I put an H there? I don't know why I put this one. This is not. So here, if it breaks, the carbon breaks. Do you see? Because it's more electronegative. This also the carbon takes it. This also the carbon takes it. Is everybody seeing this? In here, the oxygen will take the pair. In here, the nitrogen will take the pair. In here, the sulfur will take the pair. So in all of these, I'll mention this for the next part. I'm sorry, this shouldn't be here for now. I don't know why I'm thinking. So in all of these, one thing is visible and in common is that the H is going to end up positive. You agree? In all of them. So all these compounds, whether it's alcohol or amines or thiols or alkanes or alkenes or alkynes, which are our organic compounds, the hydrogen is H+. So these are sources of proton, not hydrides. Okay? So all of this will produce protons. What if we want a hydride, meaning the hydrogen is negative, not the other atom? That's where, when you're going to get to synthesis, you have to know, I need to bring an H here. Is it going to be an H plus or an H minus? So when you start looking at your compound, you have to understand which atom is the nucleophile, which atom is the electrophile. So in all of these, hydrogen is what? So in all of these, H is an electrophile. So if I want an H that's a nucleophile, what happened here? Why is H here is an electrophile? The other has what? Higher electronegativity. So what do we need? We need to have the hydrogen have the higher electronegativity. The only way you can have hydrogen as the more electronegative is to put it with a metal. Okay? So the minute a metal or a metalloid, you have to put it with a bigger atom. So if you put hydrogen with all the small atoms, hydrogen is slightly bigger, believe it or not. That's the reason you see where they put hydrogen over there. They put it above the metals, saying that hydrogen, in terms of size, is slightly bigger than all of these. That's the reason it's less electronegative. So hydrogen seems to be like a tiny atom, but it's not really tiny in terms of size. So what do I do to make it negative? Put it next to a metal, something big. Okay? So the minute you see hydrogen attached to a metal, you already understand that the hydrogen now will take the electrons. So we have, for example, BH3, BH. You have also an aluminum. With aluminum next to an H, it's a metal, aluminum. You can also use sodium. So in organic chemistry, we use these three elements. So in here, this is called a hydride. So this is a borohydride. This is an aluminum hydride. This would be a sodium hydride. So what are the electronegativity values here? For boron is 2, and hydrogen is 2.1. Aluminum is 1.5, and this is 2.1. Sodium is 0.9, and this is 2.1. So you see in all of these, hydrogen now is the smaller atom. Okay? So what happened here? The electron will move to the hydrogen. Okay? So in these particular compounds, if you see hydrogen attached to boron or aluminum or sodium, you know that the hydrogen is going to be negative. So here, in all of these, H is a what? Is a nucleophile. Okay? So it's all about acid bases. In here, hydrogen is going to be that base. In there, H is going to be the acid. So here, H is the nucleophile. Now, let's see. So not only you have to know which one is going to take the electron, you need to know which one will react the fastest, which bond will break the fastest. So if I come back here, which of these three will break the fastest? This, or this?
The top one.
Why?
It's a bigger electronegative.
So here, we're going to use electronegativity difference. You agree? But can we use this in terms of electronegativity difference?
No. Because they're all the same.
No. It's not because they're too close. Between the carbon and oxygen, these are in the same period. So remember, if they're in the same period, we use electronegativity period difference. But if they're in the same column, same group.
You use that.
So this and this are in the same group. So which one would break faster? This or this? You already forgot chapter 2 right here.
Sulfur.
Why?
Because the size is
So
bigger
the
atom.
bond is
Easier.
longer, so it's easier to break. So I want you to remember that we don't always, that's why I don't want you to think only of electronegativity. Do you understand? Electronegativity is useful, but not always. When are we going to use it? Only if atoms are in the same period. So between these two, which one is the most reactive, this or this?
The oxygen.
So you know alcohols are acidic, but amines are not as acidic. But if you compare the alcohol to the thiol, because this is larger, even though the electronegativity is much bigger here, do you see? Still this will break faster. So this is more acidic than alcohol because of the length of the bond. So you can't use one variable to explain everything. Is everybody understanding? So, but in any case, in all of them, the bond that will break is the H will always be positive. Now in here, what do we have? Are we looking at which one will be the most reactive? Which one will be the most reactive? Out of these three. Why?
Because it's two different
Maybe aluminum.
So sodium and aluminum are in the same row. So we can compare these two. Which one will break the fastest?
Oh, wait.
And if you compare these two, they're in the same group, which means which one will break the fastest? Aluminum. So in terms of reactivity, we already know that this is stronger than this, and this is stronger than that. Let's repeat, this and this, which one is a stronger one? Why?
Because there's a greater polarity or difference.
This would be because of electronegativity difference. And between this and this, what's the difference?
The size.
The size. In other words, it also has to do with metallic character. Do you remember 152? You did in lab. I don't know if you still remember that because I wrote that experiment. I used to teach 152 for years and years. In lab, we ask you to compare metallic character of elements. So in terms of metallic character, which of the three is the most metallic? I'm comparing what here? Sodium is more metallic than aluminum, and aluminum is more metallic than boron. And what do we call it in boron? Is this a metal? Is it a metal? It is a metal. So in here, we have three sources of hydrides that you're going to see in the future chapters. Either it's going to be with boron or aluminum or sodium. Okay? Now, which of these three is the most reactive? Chemically speaking, it's this because this is the most metallic. This one would be the least reactive. I just said it. Which one is the most reactive? Is sodium. Why?
Because the greatest electronegativity.
The most metallic. Which one is the least reactive? Borons, because it's the least metallic. Okay? So this is crucial for organometallic compound. All of them, not just here. Here I'm talking about hydride, and it's exactly the same reasoning with the organometallic compound. So here, sodium is more metallic than aluminum, which is more metallic than boron. Why? So as we go this way, what happens? The metallic character decreases, which means they're less metallic and more non-metallic. And you see how boron and aluminum are on the side, they're touching the nonmetals. You agree? If they're touching the nonmetals, meaning they're closer to nonmetals than metals. Okay? So if the metallic character decreases, this is the most reactive. And this is the least reactive. So in chapter 15, 16, 17, every time you're going to see a BH, it's called a borohydride, it means there is a hydride there, but it's not very reactive. Why? The boron is not very metallic, so the bond is not gonna break easily. It will break, but it's not a quick and easy reaction. So now, just thinking about the bond, but also you saw it today, for example, in the experiment, you have to dissolve your substances in order for them to react. So not only you have the chemical aspect, you also have to think of solubility, okay? So which of these would be the most soluble in water? Which one would be the most soluble in water? Sodium. It's almost ionic. So this is ionic, and you learn that ionic compounds are soluble in water. Which one would be the least soluble in water? Boron hydride. So since organic compounds are not soluble in water, what's going to happen then? If they're not soluble in water, we can't use this. Do you understand? Because this is only soluble in water. So what you have to do is make it soluble for it to react. So chemically speaking, it's the most reactive. But if it doesn't dissolve, it's going to be the least reactive. Please write it down, because these little things are important when you start studying reaction. So chemically speaking, in terms of polarity and electronegativity and size and all of that, we already know that sodium hydride are the most reactive. But what is their limitation is they're highly soluble in water. So if they're highly soluble in water and your substance is not soluble in water, they're not going to react. You understand? They're going to be in two separate phases. So this is the least soluble in water. Is that true?
Most soluble.
Most soluble in water. And this is the least soluble in water. So what does it mean? It means if it's an organic compound, the boron hydride will be more reactive than this, just because it doesn't dissolve. Okay? So these two dissolve in water and in organic compound. This one dissolves only in water. Okay, so NaH only dissolves in water, so it limits its reactivity. You can't use every substance as a hydride with sodium. And if it dissolves, it's a very strong base. So this is a very, and I can't say it enough, the hydride here, the hydride right here, is a very strong base. So what does it mean, very strong base? It's going to get rid of that electron as fast as it can. This is a very weak base. So if it's a weak base, what do we call it? In general, we are going to call it just a nucleophile. So if it doesn't really react too much as a base, we consider it as just a nucleophile. So what is the difference between a base and a nucleophile? A nucleophile means it docks with its electrons. A base, it means it grabs H+. So if it's going to grab H+, this one will grab H+ the fastest. If it's just sharing a lone pair, that's the most plausible scenario. Okay, a nucleophile is just sharing lone pairs, whereas a base is grabbing H+. So base follows more Bronsted definition, and nucleophile follows Lewis definition. So did you forget these definitions? Let's repeat. What is a Bronsted acid? The substance that donates H+. What is a Bronsted base? Accepts H+. So when we use the term base in Bronsted, term base means Bronsted, means there is an exchange of what? H plus. One accepts, one gives. When we use the term nucleophile, electrophile, what do we use? What is a nucleophile? What is the Lewis base? It's a substance with a lone pair. What is a Lewis acid? A substance with an empty orbital. So if it has an empty orbital, it is an electrophile. If it has a lone pair, it is a nucleophile. So that's the major difference. So if we're thinking of a substance as a Lewis acid, we call it electrophile. If we think of it as a Lewis base, we call it nucleophile. Why? Because there is an exchange of electrons. But if we call it a base or an acid, if there is an exchange of H+. Is everybody understanding? This is the terminology in organic chem. Yes.
With the very base, is that the whole thing or just the?
It's the hydrogen that's the base. It's the H minus, it's the hydride. Okay? The hydride is this pair is going to act as the base, the base base. Okay, so is everybody understanding hydrides? Now we're going to do the analogy with carbides or organometallic compounds, carbon containing. So here, again, in all of these substances, so if I look here, the CO, I'm going to just put by analogy the bond between C and something else. By the way, I forgot to mention the source here for hydrides that has a BA, so it's going to always be NaBH4. So it's Na, which is really Na plus BH4 minus. Okay? So when you see NaBH4, it means it's the source of the reaction is a hydride and it's a nucleophile. Here for aluminum, it's, so you have two different forms of aluminum. So we have the lithium aluminum hydride, which is really lithium plus AlH4 minus. And then the sodium hydride, that's what it is. Now this one is very reactive. We already established it's more reactive than that, okay? So this is more reactive than that. And it has 4 possibilities of hydrides. Do you understand? Each of these H's can be given as a hydride. This one, only one goes as a hydride because it's bonded to a metal. So these are details you should write. For NaBH4, only one of the H's is a hydride. Because once it gives that first H, it becomes a Lewis acid immediately. In here, it can lose many hydrides because it's still a metal, okay? So the hydrides are still going to be the negative part. The aluminum is always going to be the positive part. So this one reacts only once. This can react more than once.
You can do up to the 4.
Yeah, but we're not going to go all the way to 4. So we're going to keep that in mind, that if I see an ABH4, it only reacts once. If I see an Li, ALH4, it can react more than once. So what do we do if we wanted to react only once? Okay, so what we do, we have variations of it. So I'm going to show it to you. And one of them is very long name. So there are variations of the lithium aluminum hydride. The variations here are, the first one is lithium, and notice this. It's lithium tri-tert-butyl butoxy, tert-butoxy, aluminum hydride. So what it means, they took 3 tert-butoxy. So what is a tert-butoxy? It's a CH3, CH3O. And they put 3 of these on the aluminum, and the last one is a hydride. So what is this? Every time you see tert-butyl, it's really to make it bulky. So basically, we're crowding the space around aluminum so that it can only have 1 H. Okay? So when you see this, there's only 1 hydride that's functional. So instead of having 4 hydrides, we have 1 of them, and the other 3 are what? This. Okay? So it will be, the formula would be lithium, and then you have aluminum, and then you have CH3, 3O, 3, and then H. So you don't have to know all of these details, but just remember, if you see something like this, it means you have 3 of these, so you only have 1 hydride. So you can reduce the number of hydrides, so it only reacts once. And it will be slower because you have steric. If you want it super fast, you use this. This will happen super fast, and it goes and goes and goes. It's hard to stop. So if we want to stop it, we use this. Okay? The other one is it's also a complicated name, diiso, and for the same reason. So it's diisobutyl aluminum hydride. So the for short, they put D for di, I for isobutyl, B for butyl. So diisobutyl aluminum hydride. Actually, they put D-bulb with an L, H. So basically, the D is this, the I is this, the B is this, the aluminum is this, and the hydride is this. So for short. So if you see D-bulb, it means only 1 hydride is available. Or this one. This one is much slower. But the key thing is for you to recognize what does that mean. So let's repeat. There are 2 sources of hydrides, and you'll see we're going to have the same similar thing with the organometallic. That's why if you understand this, the other part will be just a parallel, exactly the same. So boron is slow, not very reactive, and it can only give you 1 hydride. Lithium aluminum hydride is very reactive, and it gives you more than 1 hydride. So what do we do to make it reactive but not more than 1? We use D-bulb. Okay? So it's still a hydride from an aluminum, is still a polar bond, but it only has 1 hydride, so it stops the reaction after 1 application. Okay, now let's move to the carbon-containing compounds, which is organometallic compounds, which is what is on this chapter. So the analogy here, the carbon-containing compound. So I'll tell you all of these, the hydrides and the carbon-containing hydride compounds, what they're used for. They're basically used for chapter 15, 16, and 17. And what we're going to do with each functional group, you're going to write the reaction with each one of these. Okay? So the book writes these reactions, but it doesn't explain what the difference between these reactants. And that's what I'm doing here, is to explain how are they different so that it helps you simplify it. It might look like there's one chapter, I think 16, where you have maybe 40 reactions. 40, yes. And it looks overwhelming, but if you understand the difference between the reactants, then it becomes really easy. If I have something very reactive, I know it's going to react to everything. But if I have something not very reactive, there's a limit in where it's going to react. So that's just like we did in chapter 10, when we focused on alcohols being the most reactive. And then as we went to epoxides and ethers, the reaction became less and less. So that's what's going to happen here. Okay, so now let's look at carbon-containing compounds. So in the organic compound, we have CH, for example. We have CBr, or Cl and Br, so all the alkyl halides. This goes on. Then you also have CN. Then you have CO and CS. Did I miss anything? I put CS here. So in all of these, if you look at the electronegativity difference, the carbon is the least one. So for example, carbon is 2.5 in all of that. I'm trying to give you the analogy and to show you what the book kind of wants to go into. Okay, so all of it, the carbon is 2.5. So if I look at fluorine, it's 4, then 3, so this is 4, this is 3, bromine is 2.8, and this is 2.5. You look at nitrogen, is 3, oxygen is 3.5, and sulfur is 2.5. So again, just like with hydride, in all of this, which atom will take the electron? The carbon or the other atom? So here, all of these that we studied so far, we studied these, we saw these compounds before. In each case, the other atom will take the electron. So when you see it, you have to remember that. So what does it mean? It means the carbon in each of these scenarios is going to be positive. That's the reason we could form a carbocation. Remember, in all of the previous chapters, that's what you form. When you break that bond, you form a carbocation. So in all of this, the carbon is a what? Electrophile. So C is electrophile. So if you want, in synthesis, a carbon that's positive, you use any one of these. But what if I want a carbon that's negative? Just like hydrogen, we have to find an atom that is bigger and less electronegative. So just like we did it for hydrogen, we use a metal. Okay? So that's why this chapter is called organometallic. Meaning this is the carbon part, and then it's bonded to a metal. So what are our choices here? You have compounds with lithium, okay? So in this chapter and future chapters, that's why I want you to kind of remember that. So you're going to have lithium with carbon, okay? You're going to have magnesium with carbon. I'm not giving the details of what's here. What matters is like if you see lithium with a carbon, you also have aluminum with a carbon. you have cadmium with carbon, and you have copper with carbon. Okay? In all of these, if I look at the electronegativity difference, just to be consistent, so this is 1, and this is 2.5. 2.5, 2.5, 2.5, 2.5. So for magnesium, it's 1.2. For aluminum, we already did this, 1.5. For cadmium, 1.5. And for copper, 1.8. Okay? So as you can see, in this case, carbon is the more electronegative, so it will take the electron. So in all of this, the carbon is what? Nucleophile. Okay? So in all of this, carbon is the nucleophile. Now, which of these, maybe I should write it here, sorry, because I need the space. I'm going to put C is nucleophile in all of these. So which of these is the most reactive? Just based on what I put on the board. Which one? Lithium is the most reactive. As you can see, lithium and carbon are the same row. So lithium is much less electronegative, so carbon will pull much harder. And then if you compare the others, magnesium is lower, next to lower and next to sodium, so it's slightly less reactive. And then aluminum will be less, and then these two are the same, and this one is kind of in between. Okay? But the key thing for you to know is that these are extremely these are compounds that will give you carbon that's negative. So it's called carbon anion compounds. They're producing a carbon anion. We're not going to call it carbanion for now, but it's a carbon anion. Okay, so these ones, the ones with lithium, they have a name. It's called organolithium. Okay, so the ones with lithium, they're called organolithium. These are called organomagnesium, but they have a better name for the first person organomagnesium, because the person who used them way back, I think he got a Nobel Prize for this, because most people thought carbon can never be negative. So they're called Grignard reagents. Okay. So these are called organoaluminum. These are organocadmium. And these are called organocuprate. Now these, the organocuprate, have a different name, just like the Grignard reagent. They're called Gilman reagents. Gilman is one N and one Gilman reagents. okay? So the hydrides, they don't have a name as a reagent, but these, some of them have a name. You're gonna see it grabs and this and that in the same chapter. Starters, Suzuki reagent, stuff like that, okay? Now, what are the sources? Which one is the most reactive? So you will see that if you look at the periodic table, the lower you go, the more expensive the metals are, okay? So if I have an aluminum, an organoaluminum, and organocadmium, which one would be cheaper to use? And they both have exactly the same electronegativity difference. So there's no reason to use an organocadmium if you're going to get the same result with an organoaluminum. Do you understand? Because it's cheaper. So this would be our choice in this chapter. We're not going to use organocadmium. And copper is very inexpensive. So it's going to be this, and that. Okay? So just remember that it doesn't mean that whatever you learn about aluminum, it applies also to cadmium in certain ways. Okay? But it's more expensive, so we don't have to use something more expensive. We can achieve the same results. Okay? So these, you probably are not going to see it in the chapter. They mention it a little bit, but then that's about it. Okay? So we're not going to study it that much. What was your question?
So in the organometallic, we worry less about being in different periods, more about electronegativity.
Kind of, because, and that's a good question. The transition metals, their size, if you remember in 200, it kind of fluctuates. So if it fluctuates, it's hard to know if it's really just electronegativity.
I'm confused about why magnesium isn't more reactive than lithium, because it has less of a difference than oxygen
Yeah.
and sulfur, and it's 3 times bigger, whereas sulfur is just like twice as big as oxygen.
No, but magnesium is an alkaline earth metal, and lithium is an alkaline metal. So they're very different in terms of family, whereas sulfur and oxygen are in the same group, okay? So that's the reason for transition metals. If you remember in 200, the size kind of goes in a zigzag way, so it's hard to I can explain it, but it's not the purpose of this class, okay? But it's a combination between size and electronegativity.
So we don't worry about the size
You
so
don't
much
have
if
to
they're in
worry
different-
here, because it kind of fluctuates for transition metals, okay? So is everybody understanding that they belong to different families? It becomes a different story. And you can see, this is an alkaline metal, this is an alkaline earth metal, and this is kind of, it's not a transition metal also, this is a transition metal. So each one of them is a different type of metal, and the reason they give them different names is because they have different behavior. So for us, for now, let's just look at electronegativity difference, okay? That's the only best tool we have to kind of compare them. So based on that, since I'm gonna ignore cadmium, which one would be the most reactive? Organolithium, followed by what? Organomagnesium, then aluminum, and then organo. So as we go down, we are decreasing what? The reactivity. Okay. And I'm glad you asked that question, because I don't want you to think that there are exceptions. It's not really an exception. You compare what's comparable. So when we compared, for example, carbon, nitrogen, oxygen, fluorine, the size was not that big of a difference, but the only thing we had was electronegativity, but they're all considered nonmetals. We're not comparing apple to pear, we're comparing apples to apples. The minute you start changing the family name, then you have different criteria that we don't want to compare, okay? So the reactivity decreases, which means if I put a lithium with a carbon anion, that would be the most reactive. But if I want something mild and slow reaction, to control it, I'll use the organocuprates. So that determines not only how fast, it's basically the rate of the reaction, okay? So what if I want something that's not this much, but it's not like magnesium, and you'll see why the Grignard are really a pain. They're very hard to work with, and you have a lab next week on this. So we try to avoid these because they're hard to work with. So, but I can't use this because this is more reactive, and I can't use this because it's too reactive. So what do? We combine two metals. So this is called, to use your book, sometimes we can combine two metals. One will increase the reactivity, one will decrease it. So you can play with that, okay? And it's called, in your book, transmetallation, okay? Transmetallation, you exchange a metal to another, and sometimes you can put two metals instead of one, okay? So you see the organolithium compound become organocuprate. I'm sorry, this is, yeah. So the organolithium, we transform them into an organocuprate by combining lithium and copper. So you'll see how it works, okay? So sometimes we can really play with things, reactivity, by mixing metals. So that's to show you that everything is possible if you're smart enough to manipulate the reactivity of compounds. If you use lithium, it's super nasty, super reactive, and it's not a good idea to use it by itself. If you use copper with carbon by itself, it's very slow. So what we do, we infuse some lithium in there, and it makes it kind of average, not anymore too strong or too. Is everybody understanding this? So that's basically the first part of this chapter, is to explain organometallic. But I used two for the price of one. I also explained what? Hydrogens, okay? And it's exactly the same. That's what the only thing I think is not done well in this book is they skip the hydride. I should send an email and say, please include them somewhere, because your book is almost perfect, but it misses this component. Okay, so what are the reactions then with these organometallic? Okay, so everybody understands the hydrides, everybody understands the organometallic, and you understand the difference in reactivity because of the difference in electron reactivity. And you need to know what is then a Grignard reagent, what is a Gilman reagent. We're not going to work with cadmium again, and what is an organolithium, and what is its limitation, so that when you see it, you should know what reaction it does. Okay, let's get started with these compounds. So if you remember in 152, because I remember in 152 when I talk about metallic character, I'm pretty sure students look at it and they're kind of memorizing, oh, as you go down, it gets up, and as you go to the left, it goes down. Then what? You know, it's really very important. This chapter is one of the most important chapters in organic chem, because this is the new path for organic chem. Like the Suzuki reaction you did today, it's kind of brand new. It's the end of 20th century. And so you're kind of ahead. A lot of colleges don't even touch it, don't even know what Suzuki reaction is. So this book is just showing you that in the future of organic chem is using not only organic compound, but adding some metals. So it's very interesting. But you wouldn't be able to understand it if you don't understand the difference between metal and non-metal, size, how the the sharing of electron is shifted one side or the other. But that's what you need to keep in mind constantly. When you look at a chemical reaction, which atom is taking the electron, which one is giving the electron? Because that's basically what happens in all organic reactions. If you see the arrows, it's the electrons are moving. So which one takes, which one gives, and why? Hopefully with this you understand. In here, it's always the other atom because the carbon is less, it's the bigger one. With organometallic, the carbon is always the smaller one, so it will take the electron. Here, the station, not the space station, the spacecrafts, all the ones, the Discovery and all the ones that went and came back, and some of them got exploded completely. They're made with organometallic compounds. The glass, many components, many of the material in it is made with this. So this is a huge field for material science. For those who are interested in material science, this is huge. Okay, so what are the reactions? So we're going to start with alkyl lithium, and then we're going to go to the Grignard reagents. Why alkyl lithium? Because they're the most reactive. So we want to see what are their reactions. So reaction of alkyl lithium and Grignard reagents, which are lithium with carbon and magnesium with carbon. So first, it's substitution, okay? Nucleophilic substitution. Why nucleophilic? Because we know that the carbon here is a nucleophile. So nucleophilic substitution, just chapter 9, except that instead of using alkyl halide, we're using lithium, alkyl lithium, okay? So here we go. This is an alkyl lithium. It's an alkyl attached to a lithium. And if I put it in water, what happens? Which atom is the nucleophile? Which part is the nucleophile? Which part is the electrophile? The R will take the H. You understand? Because that's the nucleophile. So what happened here? The oxygen takes the bond. So you end up with RH plus Li plus, and then OH minus. So what does it tell you? It tells you, be careful. If you're using these compounds and you put them in water, they will react with water right away. Okay? So they're nasty. Same thing with R and GX. So these are Grignard reagents, by the way, and I forgot to mention how to prepare them. Yeah. Did I skip that part? Yeah. I'll go back to it. It's okay. So this is lithium, alkyl lithium. So you know what we're talking about. This is an alkyl lithium. And this is a Grignard. So I'll put how to prepare them here. Let me just put this one. So again, if I put them in the presence of water, the R means there's a carbon negative, so the carbon will take the H because it's negative, and this goes like this, and you end up again with RH plus MgXOH. the same thing with alcohol. So with water, that's what you get. Let's try with alcohol. R Li plus R prime OH. So what I'm showing here is instead of using water, I use alcohol. So in here, which part is positive, which part is negative? This is negative, you agree? So that negative will attach where? Can it attach on the oxygen? So what is it gonna take then? The H, because this bond is not gonna break as fast as this one. So the R takes the H, this opens. So you end up with, again, RH plus Li plus, and then O minus alpha. So I can do the same with the Grignard. So both of these, Grignard and lithium reagents, you put them in water, you put them in alcohol, you end up with an alkane, which is not interesting. Because you're not interested in forming alkane in organic chem, you're interested in forming other compounds. So it's very difficult to use them if you're not working with something completely dry. No alcohol, no water. So both of them produce alkane. Now, what if we put them in the presence of an alkyl halide? So this is one type, so this is reaction with water, this is reaction with alcohol. The last one is with an alkyl halide. So what's going to happen here? Which atom has the R attaches to what? This attached to this opens. Because in this one, this R, the carbon is positive, the other one, the carbon is negative. So I can kind of hint to it. So this is always the negative. This is going to be the positive. This is the negative. This is the negative. Negative. We said it's a nucleophile. Okay? So we end up with R prime plus now I start with this organolithium, the Grignard. So again, in organometallic, the carbon is always negative. In the other substances, the carbon is always positive. Now, this is a super important reaction because in one shot, we created a bond between CC. Okay, so here it's a CC bond. In the early days, to make a CC bond takes you 10, 15, sometimes 20 steps. And here in one shot, you get the CC bond. Just like today's Lab Suzuki, in one mixing of chemicals, you create a CC bond. So every time you create a CC bond, this is called coupling. When you see the term coupling, it means you're creating a new CC bond. Yes,
Can you just show anything for the magnesium going between, the two atoms in our products? For all three of the.
I'm gonna get there.
Okay.
For now, these are the substitutions, okay? So if you want coupling, meaning you want to create a new CC bond, this is a great idea to use both. The only issue is what? If you have any trace of alcohol or water, these will happen faster than your reaction. So when we work with organolithium and and the Grignard, we have to have everything super dry. Super dry is very hard to achieve. So we're gonna make you try it. You have to do the Grignard in the lab to prepare the substance in a very, very dry environment. Absolutely no trace of water. Because the minute you have water, this reaction is more important than this. This is more important. Because water is more reactive than alcohol, less steric hindrance, and alcohol is less reactive than alkyl. Okay? Now, since I forgot to mention how do we prepare these organometallic compounds, I should go back, I'm sorry about that. So how do we prepare an organolithium, or what we call an alkyl lithium? Okay? So how do you prepare an alkyl lithium? What you do, so here, preparation. So for the first, let's say organolithium. So all you have to do is take an alkyl halide, okay, and put lithium there. Okay, so it will require 2 in terms of stoichiometry. Why? Because lithium is always plus, the alkyl is always minus, so you're gonna have an RLI, and then you're gonna have LIX. So this is simple. All you have to do, but the problem is what? You can't use water, you agree? So what is the solvent here? They put hexane. No water, and it has to be hexane that's 99.999% pure. So what we do is we put hexane, they put some sodium in there, because sodium reacts with water and takes it out. So it's a long process, making sure every reaction is completely dry, because a trace of water destroys everything. And you will see it, the percent yield will go down. Some people would have a 70% yield, some people have 20%. But that tells me immediately that it has to do with the amount of water in your glassware and chemicals. Okay? So another one is you can take an alkyl, but you can also take a phenyl plus 2 Li in the presence of hexane. So everybody understanding why hexane, not water or anything, because it will react. So then you end up with a phenyl lithium plus LiX. This reaction is super fast. Then preparation of Grignard reagents. This one, you're gonna do it yourself in lab. So again, you take an alkyl halide, like RBr, and you use magnesium metal. So little pieces of magnesium. Problem with the magnesium metal is it might have some water on its surface. So ideally, we should heat it before we put it, but you're not gonna have time to completely heat it. But ideally, I would just put it in a container and just heat it for a while. I'll ask if the lab tech can take care of that. Then here, we can't use hexane. We can't use water, so we have to use diethyl ether. I'll tell you why. And then you're gonna end up with an RMgU. So what the magnesium does, it kind of sits between the R and the B. Okay? Now, what's interesting about magnesium? It has empty orbitals. So the empty orbitals here, because it's 3s2, and you have the 3p2 and the 3d, they're all empty. So what happened is the ether, having two lone pairs, will attach here. So that's what happened, is to kind of hold it in place so that it stabilizes the magnesium. So it's sitting there, so it doesn't attach to anything else. Okay? So this is like a complex between the magnesium and the ether. So the solvent kind of docks onto the magnesium so that it doesn't take any water or anything. So that's a Grignard reagent. So we don't write the ether here, but you should know that it's really there, okay? So in every reaction here, you see we put RMgX. We don't put the ether there. But in our mind, we know that the ether is just attached to the lone empty orbitals to make sure that they don't react with something else. Then the organocuprate, because I didn't put the reaction there of organocuprate. So C, so how do you prepare organocuprate? Now the organocuprates, they use lithium with them. So they're like the Gilman reactant. So what you do, you always start with a lithium, organolithium. You see here, the starting material is always an alkyl halide, but in here, it's an organolithium. So you take an organolithium and use copper iodide. So it's Cu plus, okay, not Cu2 plus. So what happened again, the copper will sit in between, but it's going to grab two of the alkyl groups. So you need two of these. Okay? So you end up with, and then here, the solvent is tetrahydroxyCHF, which is an organic compound. And then you get R2CuLi plus Li. So how does this look? It's really an R with a Cu and another R, and then another. So you have two alkyl group attaching to the copper, and then the Li is next. Plus Li, because we use two of these, so the copper lets go of the iodine, the iodine attaches there. So every time you see an organocuprate, the formula will always be R2CuLi. See the two? That's what it is. That's an organole. Okay, so we did the coupling. So since these two are the most reactive, we start with them. And then the organocuprate are less reactive, so I'll mention them later. And if you noticed, if you remember chapter 18, there was some questions with an organocuprate. You also have it, they will appear again. So if you go back to chapter 18, you'll see that organocuprates are used. But how are they used? Most of these organometallic is to really create color. Because reacting them with water and alcohol is not interesting. So we basically use them to create a new CC bond. So every time you see an organometallic, always think we're going to create a new CC bond. Is everybody clear? Because these will happen, but we don't want you to do them. We don't want them to happen. So these are kind of side reactions. Another type of reaction, they can do elimination, addition, elimination. Actually, there is elimination reaction, but that's also in the presence of water, so I don't want you to even try to worry about it. Yes?
So our creamier reactions on the right, are those products ions like the lithium is?
Yes.
Okay.
But no, but this is more ionic than this. That's why we put it attached. Okay? Good question. With lithium, it's more ionic character than the magnesium. But you see what happened is the magnesium will take the OR and the lithium will take the H. So that's why you don't want water or alcohol. For us, the main important part is this, the coupling. Now, the other reaction we don't want is the elimination, okay? So, elimination is complicated. So I'm going to show you one. You take an alcohol. So you saw that if we take an alcohol, we're going to have an alkane, but you can also have an elimination. So here we go. RCOH, CH2. So it can be within the same molecule. You see, when you create something with an OH or right here, you know, this thing. So they're like side reactions, all I can tell you. It's not important, we don't want these reactions, but they can happen. That's all you need to know. So this is intramolecular, so what's gonna happen is this goes, because this is negative, it goes to the hydrogen, sorry. Every time there is an H, and this goes here. So you end up with RCO minus, and then CH3, something like this. And then MgBr and plus, so that's so in other words, like you can keep eliminating H's within the same bond. So let me repeat. This, and this are not the desired outcome. We don't want. All we want in all these chapters to do coupling. So organometallic are great reactant to create the coupling, meaning it makes new CC bonds. So we're going to see them come back again, not only for coupling, but they're going to also appear in chapter 15 and 16. Okay? So we'll study, remember this, hydrides and organometallic. In this chapter, they only focused on the coupling, but they also react with any CO containing double bond, CO double bond, or CN double bond, or CN triple bond. So all of these, organolithium, lignin, and organocuprate, not only they focus on, they produce coupling reactions, but they react on any CO, they react on any CN, they react on any C triple bond. So these are chapter 15 and 16. These these would be addition, elimination. So because they're all similar, they kept them in one chapter. And in this one, they focused on just reactions of coupling reactions. So let's go to some of these. I'll put them, because I put these organolithium, organomagnesium. How about here, the Gilman? So I have R, we have R, Br, just like we did here, plus R prime, 2, Cu, Li. Okay? So just like here, you see how we have alkyl halide, I can do this and this to be consistent. So you take an alkyl halide with an organocuprate, what do you get? You get R prime, same thing as this, plus RCU plus Li. So that's also coupling. So out of these three, which one is the best choice? The top, second, or the third? They all give you coupling reactions. Which one is the best? So how are they similar? How are they different? Which one reacts the fastest? So the top one is the most reactive, the bottom one is the least reactive. So you need to remember that. And that is going to be important in the choice of synthesis. So, and from now on, we're going to see many ways of preparing things. So we need to know which one is the most appropriate for what situations. So both lithium, organolithium, Grignard, and the organocuprate, which are the Gilman reagent, they all give you coupling reaction. The most reactive are the top, and as you go down, it's slower, so you can control it. You can have control over the reaction. The top two are super fast, okay? So remember that. Then, what are the most important uses for Gilman? I tell you what works the best for Gilman, which is the last one. It is best when here the alkyl is an allyl. Good. Or a benzyl group. So Gilman is highly used when you have a halogen on a C double bond. Okay? So these are, this bond is this, and this bond is this. Now, when you have this, you can have the cis and the trans. So if you want to keep it in one position, here you work with regular alkyl. Here you can, it works perfectly well with vinyl and benzene. Okay? So if I want the cis versus the trans, etc., you will see, we'll show you some different scenarios of like when to use what. Okay? So I'm going to stop here because what is left are two more coupling reactions that are not using these, they're using the Suzuki and the Heck reaction, which is something you did today. So this is kind of easy. I have to call you to give you your test by